Last time we started section 9.7 for about Taylor series, and just a kind of real quick recap. We talked about the Taylor series allowing us to basically change transcendental functions into functions of other varieties. And so in particular, they could be changed into something that look like polynomials because we have this power series expression that we're using. So we saw this power series right here that we had encountered in the last section when we looked at this last time. And then we talked about how we derive a Taylor series. It has to do with taking the derivatives. And in doing that, we noticed that we had some factorials that started to occur. And in solving for that factorial, we found a general term for the b sub k to be the kth derivative of our function divided by k factorial. And we saw that happen inside of the Taylor series. And you can evaluate at any particular point, C, or any general point C. And if you're evaluating at the particular point 0, then that's actually called the Maclaurin series. We had done one example last time, which was a Maclaurin series, because evaluating at 0 is easier generally than evaluating at other points. And so we did one with that kind of variety to start with. And eventually, toward the end, we did the same things that you were doing back in 9.6 with the power series. We were looking at the ratio test. We were finding an interval of convergence and a radius of convergence. Okay, and this one didn't actually ask for radius of convergence, but we talked about how we would do that if it did. Okay, is everybody good? Okay. I'm going to do this examples next. This is actually one, in fact, most of my examples are simply problems that are from the same problem set of homework that you work on. There's just different problems that I'm using. Because that way, if you have the ability or the desire to go back and look at an example in your textbook, I'm not doing the same example they did, so it gives you a new example to look at. This one's actually in your textbooks as well, but there is an error in the back of your textbook on this one. I'm just making you aware of it. So if you look at this later, you go like, oh my goodness, that's problem number such and such, and you go, but that's not what she got. There's a reason for that. There is an error in what they wrote down. So just to let you be aware of that. All right, so do you remember what we did last time? Take a look at your problems above. When we were looking at this particular type of a function, in this case we've got natural log of x, which is also a transcendental function. And we were wanting to start this problem and turn this into a Taylor series. What did we do first? Remember? Yeah, we took several derivatives, right? A whole bunch of them. That's how we're going to do this first. And in general, 4 derivatives is probably enough to see the pattern. If it's not, you can always take more. But let's just start with 4 derivatives and see if we can find a pattern of the evaluation points, because we're just taking the derivatives first. And then we're going to evaluate them. So what is the derivative of the natural log of x? 1 over x. And for the purposes of differentiating later, I could write that as x to the negative 1, right? Okay. How about a second derivative? Okay, good. Third derivative. Is that it? 2 first, right? The 2x to the negative third. But it's interesting that you did that, Micah, because that's exactly the error your textbook makes and how they make the mistake, yes. So see, you're just as smart as those textbook writers. No problem at all. How about the next one, fourth derivative? It would be negative 6. I'm going to write it as negative 3 times 2. Any idea why I might want to do that? You can see the factorial showing up, right? If I did this another time, you'd actually see that I'd get the 4 times the 3 times the 2. All right, everybody good so far? All right, good. All right, let's take a look then at evaluating these. Actually, we'll start out with the original function. At the c value we're working with, which is the point or the x value of e. So what is f of e? That is, what is the natural log of e? That's 1. Good. After that, we're dealing with rational functions, and let's go ahead and write them as a rational function, right? Not with the negative exponents, because it'll be easier to see a pattern, I think. Maybe not, but I think so. What would we do if we're going to work with the first one? What is f prime of e? Yep, 1 over e. I'm kind of a fan of positive exponents, too, so that's another reason why I want to write them this way. How about the second derivative at e? Right, negative 1 over e squared. How about my third derivative at e? Very good. And my fourth derivativity. Yeah, and I'm going to write it, Jordan, is it okay if I write it at 3 factorial? Will that be okay with you? All right, you do the fourth. Okay, so tell me some of the pattern you're seeing here. What's going on with what we have? What are some of the things? Yep, you're the exponent in the bottom, right? So they're all base e in the denominator, and they're all increasing every time. So that's going to be that kth iteration. We see that happening. What else do you see happening that's important to notice? Sign changes. This is alternating, right? We've got an alternating series here. All right, and we already noticed the k factorial part, which was the third thing we could take a look at that point. All right, so what I want to do next, just to give myself a little bit of space here, I want to take a look at what we would have our function value look like if we were to write this out. So if I were to write out my function would be the first value of there, which is, what do we have, 1. Plus, I would be taking the first derivative, which is 1 over e at the evaluation point, e, times what? Do you remember? Right, x minus e. All right, it's always x minus the value we're evaluating at, in this case e. Okay, great. The next one would be negative, and then I'd have 1 over e squared. And part of the power series, if you'll remember, in fact, I'll go back to it on the front side of this. Excuse me. I'm not getting it right here. Is that my b sub k is going to have a k factorial in the denominator, right? So at this point in the problem, whoops, too far. I've got that 1 over e squared, and I have, because I'm on my second term, this is k equals 0 here. This was k equal 1 here. So this is k equal 2. So I actually have a 2 factorial in the denominator. And then I've got that times that x minus e squared. So I'm the squareth term, that wasn't right, the squared term. And then I've got a positive 1 over e cubed. But I've got a 2 on the top, so let me change that 1 to a 2. And I'm going to have a 3 factorial in the denominator. And this is times x minus e cubed. And although I'm out of space, I'll try and squeeze it in here underneath. The next one, oops, is a subtraction. It's 3 factorial on top, e to the 4th. That is so not readable, I'm so sorry. And then 4 factorial in the denominator times x minus e to the 4th. And we ... It's not complete. Obviously, it's an infinite series. So far, so good? Does everyone understand where the pieces came from? So some of the pieces over here came from doing the derivative. Some of the pieces came back from that definition of what b sub k was, where I got the k factorial in the denominator. And the interesting thing to notice at this point is that I've got a factorial on top and a factorial on bottom, right? Which means they're going to simplify to what? I mean, what's going to happen with that last term where I've got 3 factorial on top, 4 factorial on the bottom? I'd have 4 left on bottom. So the factorials are going to simplify very nice and cleanly as well. Okay, so let's take a look at what happens when we're writing the series notation. So the first thing that you might notice is that it's a little bit awkward that they all have e's in it except the very first one, right? So what we're going to do is we're just going to write down the first term as 1, and we're going to look for the pattern in the rest of it. So this is 1 plus, this is my function f of x. Let me start by writing that. 1 plus, and then my series, instead of starting at k equals 0, will start at k equal 1 because I already wrote out the 0th term. Okay, so I'm going to start at 1 and go up to infinity. Now, just like on all the other ones, you know that this is x minus e, that is x minus the c value, which is e here in this case, to the k. So that part's not too bad. But we want to identify what else is happening with the other pieces. So it's probably easiest, honestly, to look at the last term, or one of the last two terms, to be able to write down what's happening. So this is the k equal 2, k equal 3. This is the k equal 4 term. So I'm going to have an e in the denominator raised to what power? Yeah, to the k power. Because on the fourth term, that k was a 4. That exponent was a 4. Okay, so that's good. It's alternating. You guys mentioned that earlier, so I'm definitely going to have a negative 1 to the k in here somewhere. And then I've also got something else. What else is going on here? Something with factorials, right? So we mentioned over here that this 3 factorial and this 4 factorial would reduce to having a what? A 4 in the denominator, right, Nathan? So like this. And that's the fourth term, correct? So what's going to go in my kth term over here? Yeah, there will be a k in the denominator. And I think I have all the pieces. Can you guys check for me? Was there anything I didn't get? Okay, everybody good? All right, so take a look back at the problem before. What did we do after we identified what the power series expansion, that is, in this case, it's a Taylor series, what it was? What did we do next? Yeah, we did the ratio test. Because we're actually there's two parts of the directions. It says find the Taylor series, which we did. And then it says determine the interval of convergence. Interval of convergence, and if we were asked for radius of convergence, come from the ratio test. Okay? So we're going to use the ratio test. They also, I was talking with Tally, they actually also come from the root test, if you'll remember from a couple sections ago. But the root test isn't nearly as helpful for these type of functions because in general things start to fall apart. You might find one that it does work for, but the ratio test works in general for all of them. So it's just easier to deal with that one. All right, so we're going to go to the ratio test. So what does the ratio test do? What do we compare? Yeah, we're taking a limit, right, as k goes to infinity, of the k plus 1 term divided by the kth term, and we're actually dealing with absolute values. Okay? Looks good. So for what I've got here, this is the limit as k goes to infinity. A sub k plus 1. Well, we talked about we don't need to write the negative ones because that's going to reduce because of the absolute value. But I do have the x minus e to the k plus 1 over k plus 1 times e to the k plus 1. And this will be times k e to the k over x minus e to the k. All right, so somebody tell me something that simplifies and what I'm left with and where. E to the what? Where? Good. Right, I've got e to the k on top. I've got e to the k plus 1 in the bottom, so that's going to reduce to give me an e on bottom. All right, somebody else.
X minus e.
Right, so I've got an x minus e to the k plus 1 on top and to the k on bottom, so I've got x minus e in the numerator. I don't know that I need those parentheses any longer. Sorry about that. And then the last thing is what? Yeah, I've got a k still on top, so I guess I did need those parentheses. And I've got the k plus 1 in the bottom. Okay, does that look all right? Now, I want to be a little bit cleaner with what I did. I know I've seen several of you in my office, and we talked about this, and we've mentioned it in class too, but just as a reminder, this x minus e does not involve k, right? The k going to infinity doesn't affect this whatsoever. I mean, it affects it, but it doesn't affect it doesn't change. Let me say it that way. It doesn't change as k changes. So this x minus e can actually be brought into the front. If we do that, it needs to stay inside of an absolute value in the front, though, because we do not know if that value is positive or negative, so we have to leave it in an absolute value still. So we're going to have this x minus e and an absolute value in front. And now the reality is that if I wanted to, I can ignore the absolute values now because k is positive. Because k is going to infinity, it's a natural number starting at 1 and going to infinity, and e is positive. So I've got everything already positive after that. So we could, yeah, if you want to. Sure. We'll do it. It won't hurt anything either way. So yeah, that's a good idea. Let's do that. Thank you. All right, so then we have k over k plus 1. Okay, k over k plus 1. What's that limit? Yeah, it's 1. All right? At this point in what we've been doing, you know how to solve that, right? What would you do if you actually wanted to show why that's equal to 1? There's a couple of things you could do. What's that? You could multiply. Yeah, multiply the top and the bottom by 1 over k. There's another way you could do it. L'Hopital's rule would work too. Yeah. All right, so either of those is going to find for us that this limit right here equals 1. So I'm going to rewrite this so that I've got now x minus e, absolute values, over e. And what I really have is times 1. Now, the ratio test says that something's going to converge when what happens? Yeah, the absolute value of all of this stuff has to be less than 1. So what this does then is the fact that the limit here was 1 doesn't end the problem for us. Some of you were getting a little confused in 9.6 then saying, okay, now what do? I got a 1. Well, you did, but you still have this other piece that's going to affect whether the value is really 1 or less than 1 or greater than 1. So we want to solve this inequality now. So we're going to take this inequality. Okay. I need more space, so I'm just going to ignore the fact that this says this right now. Okay, we'll come back to that in a minute. It's on your next page. All right, so we're going to take this inequality, and I need to solve it for the 1, or solve it for the x, excuse me. So the x and the e, rather, in the denominator could be multiplied to the other side. That's not going to affect anything. But once I've got the absolute values alone, and you wouldn't have to get them the multiply by e there, I need to solve this as a triple inequality. All right, it's not going to be centered around the origin because the c value was not 0, it was e. So that's actually why that's happening. The triple inequality says that this means that negative e is less than x minus e is less than e. If I add my e everywhere, what's the inequality become? Right, 0 is less than x is less than 2e. So the interval becomes what? 0 to 2e. And if I were asked to find it, I'm not, but if I were asked to find this, what's the radius of convergence? It would be e on this problem, exactly. And that's actually coming apart from here. This actually tells you the radius right there already, too. So this is my last piece. I'm throwing my interval of convergence.
You know, you find if it includes those bounds?
Yes, we do. That's our next step. Yep. All right, so let's see what would happen if I used 0 into my original function up here. So if x is equal to 0, I think maybe if I cut this to the other side, it'll help. Oops. Okay. So if x is equal to 0, this summation from k equal 1 to infinity of negative 1 to the k. And then I've got the k in the denominator. I've got an e to the k in the denominator. And then I'm going to now have a negative e to the k over here when x is 0, right? Oops, that should have said x equals 0. I'm sorry. X equals 0 is my first end point. So how is all this going to simplify? Yep.
And you can simplify e to the k is, 1 over k, which is divergent because it's harmonic series.
Wouldn't it be negative e to 2k?
No, but that's a good question. So properties of exponents say that if I have the same exponent, I can multiply the two bases together. So, but the exponent stays the same. And you know that to be true because you've seen this exponent rule that says something like this before. You usually see it written like this: a b to the m equals a to the m b to the m, and that's the property we're using, but in reverse. We're starting with the side that looks like a to the m, b to the m, and then we're moving backwards into the other side. So the negative 1 to the k and the negative e to the k, those will become e to the k, just like Micah said, which will reduce with the e to k in the denominator. And now this is a harmonic series. Yes? So this is harmonic, so it diverges. All right, my other term, or my other endpoint that I need to test is the endpoint at 2e. So this is the summation from k equal 1 to infinity of negative 1 to the k over k e to the k. And then I'm actually going to get a positive e to the k because I'm going to have 2e minus e, which is going to give me e to the k. So on this one, I don't even have to use those exponent rules that I just did before. It's actually much cleaner with the e to the k's reducing. So I now have negative 1 to the k over k, which is different than I had before. Will this converge or diverge?
Converge.
That actually converges. Why?
This is the alternate series test.
Yeah. The alternating series test says that if I have, ignoring the part that alternates, if I have the limit of that sequence going to 0, which it does, right? 1 over k goes to 0, then if it's alternating, then it's going to converge. You guys remember that? I hope you will. It's important. The fact that it's alternating makes all the difference in the world on that one. All right, so this actually becomes the summation from k equal 1 to infinity of negative 1 to the k over k. And this converges by the alternate or alternating series test. So my interval that started out 0 to 2e is going to not include 0, and it's going to include 2e, which means my interval, coming back over here now, will have a bracket right here. Is everybody good with that?
Okay, so what are we saying happens between 0 and 2e?
We're saying that if you have an x value between 0 and 2e, that this series is going to converge. So let me write that down, in fact, too. This is my interval of convergence. So this will converge when x... Okay, let's try that again. I don't think purple's a good color since I've got so much purple on the screen already. This will converge when x is an element of 0 to 2e. So if x is any value between 0 and not including 0, all the way up to 2e, but including the 2e. If x has any of those values, this Taylor series is going to converge. Okay. All right, one more question. You guys are going to like it. It's very clean and straightforward. All right, so this little part that I marked out at the top is actually on your paper. So you can look at it and read it there. But on page 595 in your book, there's a list of Taylor series. And on your test, I'll give you that list. I'll just give you a copy of that piece of paper. From that page. It's a list of Taylor series and their transcendental function notations that you can use as a reference to do the problems after that. Okay, and the direction set will look very much like this for the problems where it is using that feature. It says use a known Taylor series, hence the ones that are on page 595, to find the Taylor series about c equals 0. What's it called when a Taylor series is centered about c equals 0? Maclaurin series. So this is specifically a Maclaurin series. Then it says for the given function, so our given function down here is sine, and then find its radius of convergence. All right, so the first thing I'd like for you to take a look at, and you're going to have to tell me because I don't have my book. On page 595, there's a transcendental function for sine, right? I mean, there's a Taylor series for sine. So the sine function, just plain old sine x, what does it say the summation is? On page 595.
Okay, 0 to infinity, negative 1 to the k over 2k plus 1 factorial of all that, and times x is the 2k plus 1.
Did I get it written right, Micah?
Yes.
Does that look okay? All right, so you ready to see how beautiful and easy this is? What do you think you might do to find sine of x squared? Say again, Tally? Yeah, in the other side of it, right? It's exactly what we're going to do. Everywhere we have an x and there's only one place, we're going to change that x to 2x, or to x squared, excuse me. That looks a little awkward. There's no reason to have that exponent to an exponent, so we'll rewrite it one more time to just clean that up a little bit. So this is the series k equals 0 to infinity of -1 to the k over 2k plus 1 factorial raised to what power of x, or x raised to what power? Yeah, sorry. 4k plus 2, exactly. Now, we haven't done quite all of the directions, though. We found the Taylor series, but we're also supposed to find the radius of convergence. So what was the radius of convergence that it told us in that table for sine? Yeah, and that's actually an interval of convergence, right? This one actually says radius, so we'll use the infinity. Okay. So what's going to happen if the x value is allowed to go from negative infinity to infinity? How's that going to change for our function? It won't. It'll be the same thing, exactly. So my radius is also infinity. So this set of problems is really clean. It's just I'm using that table page 595 to identify the pieces that correspond. Any questions on this one?